something. Here, the chocolate jar.
Okay, let us start. So I promised to define a non-standard mathematical universe, so I'm going to do it. So we had the following system. We have system S, union Si, where S0 was a basic set. No, it contains, for our purposes, real numbers and maybe something else what we need. And Sn plus 1 equals Sn union P of Sn. So union of all this set is the set S check, which is called superstructure based on the set S0. It is one element. So this superstructure is the playground of our mathematics, as I explained. So any object of mathematics, any set, any relation, any operation is contained in this set. Now we had a set I, which can be called index set, which is completely unrelated to this set. So this I is not in our superstructure, and it has quite different nature. No, elements of I are denoted by I small. Now we have F improper ultrafilter on I. So F is its elements are, let me write it. It is a system of some subsets of I, not all, but some of them, which satisfies the properties, three properties, that if some set is element of F, then any larger set is also element of F. If we have two elements of F, then the intersection is also in F. Then the third, that empty set is not element of F, and the whole I is element of F. And improper means that no finite set is element of F. So to exclude some trivial and not interesting examples. And now I define the following new thing. Consider a function f of I. So elements of f of I is a function with values in our superstructure. F, so from I to our superstructure. And not all the functions like this, but only the following functions having the following property. Let us Zn is the set of the function f of I such that f of I belongs to Sn for almost all I in I. Almost all I means that the set of I in I such that f of I in Sn belongs to our superstructure F. Yeah? Or that measure of this set I such that f of I in Sn is 1. No, measure of a set is 1 if the set belongs to our ultrafilter. No, otherwise it is 0. Yes, so it is sort of indicator that the set belongs to ultrafilter. And as I explained last time, this measure on ultrafilter, it is measure defined on all sets, and it is really a finitely additive measure. It's not sigma additive, but finitely additive. So the on one hand, it is not like say Lebesgue measure, it is just finitely additive. On the other hand, it is defined on much larger class of sets, namely on the all subsets of I. Yeah, so Zn, this is a great restriction on these functions because, say, if our set I is the set of natural numbers, positive integer, yes, and each element f of I belongs to S number I, then certainly there is no such n that it contains all images of I. Yes, we are going higher and higher up this ladder. So this means that such a function is not in the class Sn for any finite n. And Z is union of Zn, and from 0 to infinity. Okay, so this is one. So we start, we take these functions, yes, and these functions are the material to construct our non-standard world, non-standard universe. Now let us start from the function from Z number 0. Yeah. Z0. This means that f of I belongs to S0 for almost all I, or almost everywhere. So we start from this function. And we naturally has the following relation, we write that if f and g in Z0, we write f equivalent to g if f of I equals g of I almost everywhere, for almost all I. So two functions which coincides almost everywhere, we naturally call them that they are equivalent. No, obviously this is equivalence relation, so f is equivalent to f equivalent to g implies g equivalent to f. And the last is f equivalent to g and g equivalent to h. Then let us compare both the function f and h with g. F and g are different on some set of measure 0. So f different from g on a set, say A, in I, measure of A is 0. G different from H on some set B in I, such that measure of B is 0. Yeah. Then f different from g or g different from h, so one of this, at least one of two, on say A union B. Yeah, but we already know that measure of union is less or equal than sum of measures. It is equal if they are disjoint. Otherwise, it can be less. So measure of A union B less or equal than measure of A plus measure of B, which is 0. No, so this means that measure of A union B is 0. So one of these inequalities holds on measure 0, at least one of them. Yeah. So measure of I minus A union B is 1. F equals G and G equal H on I minus A union B. Yeah? So this means, and if both happens, then F equal G equal H. This means that F equal H on this set, I minus A union B. Yeah? So a measure of this set is 1. And this means that F equal H almost everywhere, for almost all I. Yeah? No, it is a rather simple reasoning, but it is an important point, therefore I did it in detail. So this means that if F equivalent to G and G equivalent to H, then F equivalent to H. So we have three properties of this relation, equivalence, saying that this is equivalence relation. So this equivalence relation defines a partition of the set, which set S0, just a minute, the set not S0 but Z0. So F is and G and H are elements of the set Z0, of the set of functions on I with values almost everywhere in the set S0. So this means that this is equivalence relation on S0. Yes? So the set of G in Z on, say, Z0, on Z0 such that G equivalent to F is denoted, let me denote by MF. So it is equivalence class containing F. Yes? And the set of all these equivalence classes it can be denoted by Z0 factorized by this relation, or let me denote it by Y0. So we define this new object. It is already a big object. It is the set of equivalence classes of functions on the index set I with values in S0 by this equivalence relation, which is defined by the ultra filter. Very good. And now let us do the following. We have this set W0, it is a set. And now let us define W1 equals W0 union P of W0 and so on. Wn plus 1 is Wn union the set of subsets of Wn for all n. Yeah, so we define another superstructure which is visibly much larger than the previous superstructure S. So union of Wn, when n from 0 to infinity, let me denote it by W check. So it is another superstructure. Now this, what I'm going to do, this is still not what I'm looking for. So we have, for now, we have two sorts, two big, I would say, fields. Let me also denote Z check equals union Zn, and from 0 to infinity. So let us look. Elements of W check of this superstructure is some elements of this superstructure is some set. Each element is a set. Or yes, on W0, at the level W0, we don't regard them as sets, we regard them as individuals, yes, to get closer to, it is a function, it is a complicated object, but what is a function? The function is given by its graph, some subset in the Cartesian product of what? Of I and S0. But I is not in our universe S. Yes, I is completely unrelated. And we'll see how much it is unrelated later, if you will survive it. Yes, so it is, it is a quite different thing. And so this W0 we will consider as a collection of elements, not as sets. No, in sense that we never ask the questions about them as sets. We simply regard them as individuals. Now, what is Z? Z is a collection of functions. Yes, no, functions with values either in S0 or in S1, S2, and so on. So these are functions, these are sets. Yes? So we have to define new, yes please.
So you said the first law of the superstructure is the union of all natural numbers.
Natural numbers, yes.
Is it the same types of things?
Yes. No, when I write union over n, it is from 1 to infinity. Oh. And here I also include 0.
0, yes.
Yeah. So this is this set. So let me remind again that Z0 equals the set of function f of I I in the set f of I belongs to S0 almost everywhere for almost all Zn equals the set f from I to Sn almost everywhere. In the sense that the image is in Sn for almost all I. And Z check is a union of Zn and from 0 to infinity. Then I define the equivalence relation F equivalence to G if F of I equal G of I for almost all I, and almost all means in the sense of the measure which is associated with the ultrafilter. So it is F of it is equivalence relation. Now Z0 factor over this equivalence relation is called W0. Yes? No elements of W0, let me write MF equals the set of all G in Z0 such that G is equivalent to F. Yes, these are equivalence classes. So W0 is collection of these sets, these elements MF, equivalence classes, F in Z0. So this is W0. And and then I define the superstructure Wn plus 1 equals Wn union with P of Wn, n equals 0, 1, and so on. And W check equals union Wn, and from 0 to infinity. Yeah. So this is another superstructure such that its basis is the basic set is W0. We can start from any set. No, in this case we start, which is somehow associated with S0. Because Z0 is the set of functions which take almost everywhere values in S0. That's it. And now, again, you have this set Z, yes, and we have this superstructure. What I am going to do now, I define some, I would say, substructure in this superstructure, not all of it, but some of it, some sets of it, which will form our new mathematical universe. Yeah? And to this end, let me consider the set Z1. So for Z0, I define corresponding equivalence classes MF. Yeah? Similarly, I can define it for Z1, Z2, and so on, simply replacing here 0 by 1 and so on. But in fact, we have to do otherwise. So this is not what we need. So we need to do the following. It will be more interesting. Suppose we have some f which is in Z1. Yes, I go next step. F is in Z1. What does it mean? It means that f of I f is a function is in S1 for almost all I in I. Yes? And to avoid trivialities, I write better f of I belongs to S1 minus S0 for almost all I. Yes, because if it is in S0, we have already defined. So let us go one step up. And now I am going to define some set which is called a set MF. For this F which is now in Z1. And I give the following definition. Which is the central M if F in Z1, then define MF as the set of the following function G from I to S0 such that G of I elements to F of I for almost all I in I. So no, let me draw a picture. Suppose this is I. No, I is say these points. So at every point I, we have some set. No, say these segments. Yeah. So this is I, f of I. F of I is a set. Yeah? And now we define G of I such that G of I is element of F of I. Let me draw it like this. So this is a sort of graph of so this is G of I. G of I is element of F of I. So F of I is some set. Yes? F of I is for almost all I, it is a set. Not element, but set in S. So G of I is element which belongs to F of I, yeah, for almost all I. So here I omit several values to show that maybe not everywhere, but almost everywhere. So this is MF. No, you can imagine that there is a lot of such function. So MF is a set. What is MF? MF, it is written here, is a set of this function. this function g from I to S1 of set of g in Z0, yeah, such that g of I belong to f of I almost everywhere. This means that MF, just a minute, if G changes, if we change G at the set of measure 0, yes, then we have to, we change G at the set of measure 0, then we have the same element if you factorize it by this equivalence on Z0. Yes? So this means that MF belongs to MG belongs to W0. And G is equivalence class of G, and W0 is the set of these equivalence classes. Yes? So here we have MF. Let me rather write MF is the collection MG in W0, G of I, F of I, almost everywhere. So MF is a set, yes, a set of element of W0. Yes? And the set of all sets of W0 is called W1. Somewhere here was written W1 equals W0 union the set of subsets of W0. Yeah. So MF is in W1. Yes, please.
Wouldn't MF be the union of all MG, and W0? Because if I understand correctly, MG is itself an equivalence class.
Yes.
And since MF is defined as elements and not...
Let me write. G such that G in Z0 and so this way we found for any F in Z1, yes, we found MF in W1 by this construction. And we can repeat it further. So if F in Z n plus 1, we define MF equals the set of MG G such that G in W n and G of I belongs to F of I almost everywhere. So f in Zn plus 1, this means that it is a function with values in Sn plus 1. Yes, S is the structure which started from. It is S0 union with P of 0 union with P of S0 and so on. Yes? So we have climbed a little bit to the ladder, try to make climb from Wn to Wn plus 1. This way we define, suppose we have already defined what is Wn, yes, and then we define Mf, this set of such Mg now is Wn, so that if it is in Wn, yes, so so G in Zn. So it is a function from I to Sn, yes, such that Gi in Fi and F in Zn plus 1. So Zn plus 1, it is the function with values in sets of elements. Its elements of this set are elements of Zn, because Zn plus it is elements of Sn plus 1 are the sets with element in Sn. So we're going higher and higher. Yes, and so it makes sense that G of I, G is element of Sn, yes, and Fi is a set of elements of Sn. Yes, so it makes sense that element of Sn is element of a set of Sn, no, of some Sn, and this holds for almost all I. No, okay, it of course it is, if you compare this and this, you see that they are defined, I would say, uniformly. So it is particular case so Mg is yes, and G for G in Zn, this means that Mg in Wn to make it sound equally.
So if I understand correctly, like the equivalence class is just for the first step W0, and after we just define MF as a set, as a clear set, not an equivalence class or something.
Yes. Yes. So in the first step, the elements are equivalence class, which are sets. Here we have also sets. Yes, but definition goes differently the initial step and further. What we reached? We reached now that for we started from this function, which classes this function defined z0, z1, and so on. And now for these functions, we defined the sets. Yes? And these sets are our elements, are elements of our universe. So the sets W. No, it is, of course, far from obvious and requires some effort to understand, I would say to comprehend or to absorb. But nonetheless, this is the, I would say, solid nut we have to crack. And so, W, which is union of Wn, and from 0 to infinity, is our new universe. It is our new universe. Yes. No, I would say that this construction appeared relatively early, I think around 1920, in different relation. It was used to construct first non-standard model of arithmetics of integer numbers. And then it was adapted for the general construction of non-standard mathematics. Yeah? So, okay. And now let us go further and I write you some properties of this new model, which look quite, I would say, innocent and simple, while maybe they are not so. So again, we have two sorts of, I would say, objects. One are the functions, f of I, yeah, which are in Zn. No, let me say in Z. So f from I to S. And Zn equals set f such that f of I in Sn almost everywhere. Z equals union Zn. It is on one hand. On the other hand, we have the strange objects MF, which are elements on W. So for any F in Z, we have some MF we have defined. So M Z F in Zn, then MF in Wn. And W equals union of Wn. So we have two, I would say, sorts of objects. And now the following properties. Let me say theorem. MF equals MG if and only if, let me write here, MF equals MG if and only if F of I equals G of I almost everywhere. In all set, F and G belong to Z. Now, if they belong to Z, they belong to some Zn. No, F belongs to Zn1, G to Zn2. No, so automatically it belongs to Z maximum and 1 and 2. And so, in this case, MF equals MG in the sense of all this definition, if and only if F of I equals G of I almost everywhere. Second, MF is element of MG if and only if F of I is element of G of I almost everywhere. So let us look at this. MF and MG, by our definition, if you look at the definition which was here, are sets. Yeah? F and G themselves are functions. So again, we associated to each function some set. Yes? And in these sets, there is this relation between them. This is if the functions are satisfy this. What does it mean? Fi element of G of I. In their turn, F and G are functions with values in sets. Or no, F may be in elements, but G certainly in sets, but because otherwise this is impossible. Yeah? So F element of G, F of I element of Gi for almost all. So it makes perfect sense. And this also makes sense because MF and MG are sets. Yeah? And 3 MF subset of MG if and only if F of I subset of G of I almost everywhere. No, this makes sense if f and g values of f and g lie in Sn for some n more than 0, so that they are sets, and it makes sense that they are sets. So this means that the properties of these sets are, say, models or reflect the properties of the functions. Yeah? But the proof is not hard. It is, I would say, tautological. But you have to disclose all brackets in the definition, and then you see that it is true tautologically. Yeah, so let me not be fixed on this, and I want to pass to the next statement, where I want to show what happens here. The next theorem is if f mf are always sets, all sets beyond W0, where they are regarded as just elements and not sets. Yes? Then, no, even if they are elements, then we can form their pair. Yeah? So consider the pair MF MG. It is a pair of two sets which exists. Yeah? This pair is also, no, it is a set of two elements. Yeah? Now, is this set in our collection? W check. Yeah? So, does this set appear from some as an equivalence class of some function? Yeah? So, the theorem says that equals theorem MF MG equals MH if and only if f of I and g of I are equals h of I almost everywhere. A little bit mysterious thing. So we have two functions, fi and gi. Yes? No, to be sure, let us suppose for a moment that they are in Z0. So f and g, they are mapping I into S0. Yes? I don't, here it is not very much important that we are here we can be S1 and so and so. So anyway, automatically this is already in S1 for any I. Yes? And now consider, so what is Fi, Gi? So it is Mf, Mg. We have to consider or the pairs Fi gi, yes? And we have such that they are in this means that Fi in Hi Gi in Hi and no other elements in Hi. Yes? This means that Fi Gi equals Hi. So Hi is a set containing just f of I and g of I. Yes? One moment. F and mg equal
you can look at what MH is directly. I think it might work.
Yes. So let us consider what is MH. Okay, H of I equals F of I, G of I. Yes? Now, what is MH? For every A, for almost every I, we have a set of two elements, F of I and G of I. So, MH is the set of functions such that for any I, it is either f of I or g of I. In the set of functions, say, h of k of I, such that k of I equals equals f of I, or ki equals g of I. So just one of two. And now it is for almost all I. Almost all mean that there may be some negligible set.
Wouldn't it be like MK?
Excuse me?
Wouldn't it be the sets of MK? Maybe I'm wrong here, I'm not certain. Like the sets of MK such that K of I, if...
No, this function, just a moment. H of I is a function with values in sets. K of I here is a function with the values of elements. So every value at every I is either f of I or g of I. So they are different things. Okay, and now let us do the following. For any function k of I, for a fixed of I, define the sets A and B subsets of I. Such that K of I equals F of I. Yeah? And B K of I equals G of I. Yes, we have two sets. So we have these two sets are disjoint. No, if F different from G. Yes, I don't consider the case that somewhere they can coincide. Suppose F and G are different. Then we have B is empty set. Union B is the whole I, because for every I small we have either K equals F or it is G. So if a function may take only one of two values, for some I it takes this value, for some time this. So we have definitely a partition into sets of the set of all indices I. So what does it mean? We have the property of ultrafilter that mu of A equals 1 and mu of B equals 0, or mu A equals 0 and mu of B equal 1. Yes? Because we have a partition of I into two non-intersecting sets. Yeah? Okay, if you don't like, we can say that if somewhere F equals G, then we join this I to the set A. G and F of I is different from G of I. Yes, this way. So this way we take all elements where Ki equals Fi, or and here we have Ki equals Gi, but not Fi. So if it's Fi, we bring this I to the set A. So this means that for almost all I, we have either f equal either k of I equals fi or ki equals gi. So let me write it. For almost all I, fi equals ki fi or ki equals gi. Yeah? No, this means that k, in other words, k, I would say nk equals mf or mk equals mg. Yeah? Here is the great role of the ultra filter property, that any set is in the ultra filter or its complement is not both but one of them. Yes, and so here for any sequence k of I, we have that is k of I. In fact, its element mk is either mf or mg. Yes, and so the set of all such equivalence classes for k consists of two elements, mf and mg. No, simply because we can take k of I equal f of I for all I, so it gives you mf, or k of I is g of I for all I, it will give you mg, yes, and nothing more. Yeah, so this proves this great theorem. So the theorem is again that mf pair mg equals mk if mh and only if h of I equals f of I g of I for almost all I. Now, to this I add two other theorems which are proved the same way. We use this. So let me call next theorem that mf mg, the ordered pair, equals mh if and only if h of I equals ordered pair f of I g of I almost every. No, let me recall that fg is the following: f and here fg. Yes, so it is this pair, non-ordered pair of these pairs. No, this is single element set, which is pair FF. Yeah. So here we just iterate this reasoning. And the last theory today is that MF MG equals MH if and only if F of I restriction on G of I equals H of I almost everywhere. Yeah, so in this case it makes sense if F of I is already an ordered pair and G of I is the first term here, it is this term here, and then the second, this G here is this result of this restriction. Yeah, so here we have several particular cases when it is well defined. It's well defined if there is one and only one element like this. If there is more elements in this, because here F is in general some relation. If you have more than one, then it is just empty set. So we have to, it is not defined. If there is none, it is empty set. If this is no unrelated thing, not relation, where G makes sense. So it's also empty set. So every time when it is not defined, it is the result is empty set. And so we simply go through these particular cases, but it is no just mechanical work. So I gave you just a sample of this reasoning in the last previous theory. So this shows that it has our model, there is some relation, close relation between these two, I would say, sequences of objects. On one hand, there are functions, on other hand, there are sets. Yes? And next time, I hope to make the last effort to explain our model, yes, and then we'll go further already how to develop our analysis and use it. So this model has a great resemblance to our usual analysis, usual mathematics, I would say, but it has new features, namely infinite elements. And this is what I'm going to explain next time. Okay, so let us finish today, and if you have some more questions, maybe first you will look again at the movie which I will send you. Not you, you have no problems with finding it on YouTube. No problems. Okay, so I will send it on YouTube and you will see. So have a good time.